The focus of the lesson today is on exponential functions, and our goal is going to be to use the law of exponents to be able to simplify problems, a skill you're going to use a ton in calculus. The first thing we'll talk about is just defining an exponential function. An exponential function is in the form of y equals a to the x power, where a is a positive real number not equal to 1, and we're raising the exponent to a variable, in this case x. To find an exponential value such as that we're not used to, that's a situation like 2 to the square root of 2, we can plug it into our calculator just the way it appears, like I have there in red, by using our square root button, or we could use a caret button if we wanted, in raising it to an exponent such as 2 to the 1/2 power, if we wanted to find the square root of 2 instead of using the square root button. Our laws of exponents, which we learned in Algebra 2 that I want to review with you to be successful today. The first one, if we have the same base and we're multiplying, we would add the exponents together, so we would have a raised to the x plus y power. If we take and we're taking an exponent raised to a power, we multiply the exponents, so it'd be a to the xy power. If we're dividing and the bases are the same, we would subtract the exponents, so it would be a to the x minus y power. If we take and have two numbers being raised to the same exponent, there'll be times in more complex problems it would be valuable to split those into two different exponents. So we could change this to a to the x power times b to the x power, find them separately, and then multiply them together. Negative exponents, if you recall, we take and flip it either to the denominator. If it was in the denominator, we'd flip it up to the numerator. So a to the negative x power is the same as 1 over a to the x power. Any exponent that is a 0 automatically gives us 1. So no matter what the number is, a just stands for a real number. If we raise it to the 0 power, no matter what the number is, we always get 1. And then our last property I want to talk about, we just mentioned a little bit with the square root of 2, and that would be fractional exponents. So a to the xy power is the same as raising a to the x power and then taking the yth root of it. Now that we have our exponential rules, let's try to do some application problems with them to be able to solve. So here's a problem with some real numbers. Now if we have the exact same base, x for both of them, we would just take our exponents, so we would have x to the 15th power, because it's just 7 plus 8. Where if we take and we raise it to a power, we'd multiply the exponents, so that would be x to the 56th power. Next we have 2 raised to the negative third power. Remember, negative exponents mean to write it as a fraction, so that would be 1 over 2 cubed. And we know that 2 cubed is 8, so that would be 1/8 for the negative exponent. For x cubed times the square root of x, we can think of that as a multiplication with the same base and change the square root to a fractional exponent. So we can think of this as x cubed times x to the 1/2. And if we are multiplying and they have the same base, we'll add the exponents. So if we change 3 out of 2, that would be 6 halves. So 6 halves plus 1 half would be 7 halves. So that would be x to the 7 halves power if they wanted you to write it in as rational exponents. If they wanted you to write it in root form, you would write that as x to the 7th and then the square root of that. So either one of those answers would be correct depending on the form that they want you to write it in. Usually, in calculus, they'll want you to write it as rational exponents, so they'll have you write it as x to the 7 halves power. In number 5, we have x to the negative 2 power, which we would then obviously want to move up. Since it's in the denominator and it's negative, we can pull it up, so this is the same as 2x squared over 3. In number 6, we have 9 that has the same base. So the exponents we would add together, and 1/3 and 5/3 would give us 6/3. So we'd have 9 to the 6/3 power, which is obviously 9 squared, or 81. Number 7, we're dividing. And with this particular one, if I want to divide two polynomial functions, if you recall, I have to take that 3x squared and I have to divide it into each one. And then I can apply my exponent rule. So I could take 10x to the 5th divided by 3x squared plus 3x cubed divided by 3x squared plus 9x divided by 3x squared. Since the bases for the x are the same, I could subtract the exponents, and that would be equivalent to 10/3 x cubed, or you could write 10x cubed over 3. In the next one, the 3's would obviously cancel. 3 divided by 3 is 1, and then we would just get x, subtracting the exponents. And the last one is in simplest form. I forgot my 9x, excuse me. We could take the 3 into the 9, which gives us 3. And there's two ways to write this. If they want you to write it in the numerator, it would be x to the negative 1 power. If they want it left as positive exponents, then we would write it as 3 over x. And there's our final answer. For the next problem, we have a negative exponent. Again, we have the same base with the x's if we divide them. So if we take this one step at a time, we could take and think of this as 3/3. So if we take 3/3 and we subtract 2/3, that would be 3/3 plus 2/3, which would be 5/3. So I would get 3x to the 5/3 power. Dividing the second part of the polynomial functions, if I take the x squared and the x to the negative 2/3 power and I subtract them, I can think of x squared as 6/3. So it would be 6/3 plus 2/3, which would give us 8/3. So it'd be plus 4x to the 8/3 power. Finally, our last one has fractional exponents as well as negative exponents, and you can decide which order you would like to do those in. If I want to think of the negative exponent first and I want to deal with that part, I can look at it as 27/8 to the 2/3 power. Remember, the third means it's the cube root. The 2 means that each of them are squared. It would obviously be easier to take the cube roots first if I can, if they're perfect cubes, and then square them, than to try to square them and then take the cube roots. So I'm going to choose to take the cube root of 27, which we know is 3, and the cube root of 8, which we know is 2, and then if I square each of those, that would give me 9/4 for my final answer. Those are your sample problems to follow. What I'd like you to do for the remaining part of the class period is work with a partner or with your group if you'd like on the worksheet. There is going to be some that are going to get even more complex than these, but I want you to get a good grasp of simplifying exponential functions for when you are working in calculus and throughout the remaining part of this chapter. Have a great day, everyone. Love you guys.